So in 2D, we're also going to work with a model problem like we did in 1D. And we'll see later that the model problem can represent many physical settings. So this is our governing equation. Of course, if we write that in vector notation, if A11, A12, A21, and A22 form the coefficients of a tensor A, this is, simply the divergence of A times the gradient of U. So that equals some right-hand side. What do we call that equation? Heat equation? So here U, it's a 2D problem, so U is a function of X and Y. Right. And the AIJs are the data. So that's our material properties. And then we'd have some boundary conditions also. Okay. And this equation models heat transfer, irrotational flow, of an ideal fluid, it also models groundwater flow through permeable geology. It also models electrostatics and some other things. Of course, this is what we care about. So the weak form of our model 2D equation, because it's 2D, nothing's changed. Our three-step process. Move everything to one side, which it already is, multiply by a test function, integrate over the body. Okay.
The test function is now 2D.
Yeah, so the test function would be a function of X and Y.
So now we have a double.
I said integrate over the body.
Yeah.
The body's 2D now, so yeah, it's an area integral. So we're going to integrate over the domain, test function, where I've just replaced those terms in the parentheses above with F1 and F2. So what's another physical word for what we would, these F's? So if we're talking about like flow in a porous media, I would say the divergence of the what? If it was flow in a porous media, A would be K over mu times the gradient of P. Right? What is that? It's like Darcy's law, right? Which Darcy's law relates pressure gradient to the flux, right? It's flux. So these are the flux terms. All right, so here's our integrate by parts step. But we're going to do something. First, let's look at these terms. Look at these identities. We can rewrite that like this. And likewise for the other one. Now I'm going to write down the divergence theorem again. We used it when we were deriving, earlier in the class, when we were deriving equations of motion. Basically, divergence theorem says that I can transform the volume integral into a surface integral like this. Where ds is the surface, the boundary of the volume, right? And the nx and ny are components of the unit normals to the surface. So, in other words, the unit vector n hat is equal to nx ex hat plus ny ey hat. And so, using the if we go back, we're going to use the identities for the partials on these fluxes. we're going to use these first two identities and then use the divergence theorem on these terms and plug everything back into the equation, okay? And with that, we'll get I'm just going to squeeze this down a little bit to make room. So this is a volume integral, dx dy. And then we have the surface integral. Right. So our divergence theorem really is the integration by parts, right? So if you notice, what we had before was a test function times partial x of f1, and f1 included partials. Therefore we would have ended up with second derivatives on u, right? But what we did was we integrated by parts to shift some of the differentiation onto the test function, so lowering the continuity requirement on u, just like we did in 1D, okay? But it generated these boundary terms. So in 1D, we had these terms that were just evaluated at the endpoints, right? But now we have terms that are evaluated at the endpoints of a 2D thing, body, or the surfaces. So that's what this, we have this surface term that comes up. And of course then, I mean, this is really where our boundary conditions go. So we would, like in other words, you know, if we have no flux, then this is all zero. Right? So a lot of times we just say that this whole integrand, we'll just define it as Qn, so the surface flux. Yes, right here. By the way, just as a little aside, I don't think in 1D and even in scalar fields problems, it doesn't matter. You know, when I introduced, I said 3-step process. Move everything to one side, multiply by a test function. Well, in 1D and in the scalar problems, it doesn't matter. You can multiply by a test function. But when we go to vector fielded problems, now we have a vector fielded test function. And we're multiplying vectors times vectors, or matrices times vectors. And it does matter which side of the equation you multiply it on, okay? And ultimately, you can still solve for it. I mean, in the end, if you keep track of everything, it doesn't matter. From that sense, it doesn't matter. And you keep track of everything, you'll get the same exact answers in the end. But what you'll get is if you multiply by the test function on the right, you will end up with your definition of the stiffness matrix as we define it will be actually the transpose of, it'll be the transpose of what we will define, okay? So just as in habit, and that's why I wrote it there, okay? Let's just get in the habit now of always, when we multiply by a test function, let's do it on the left-hand side, okay? If you do it on the left-hand side, everything will always work out, okay? And you won't have to transpose your stiffness matrix. So I should add that to my three-step process to be consistent. Is multiply by a test function on the left. But of course, it doesn't make a difference until you get to vector fielding problems. All right, so if we write that down, this finally is our weak form. And if we want to write it, we can look at the bilinear terms. So then we have, we can write the whole thing by like this. Now the only way that B is symmetric, the only way B will be symmetric if A12 equals A21. Right. So if this is